Welcome students to a new lecture of electronics series, and in this new lecture we will learn the most important concept in electronics, that is the concept of load lines. See, this is a graphical representation. This is a graph, basically a current voltage graph. Graphs are inevitable in physics. These graphs, whenever we are plotting graphs in any section of physics, whether it is electronics or whether it is quantum mechanics, whether it is statistical mechanics or any branch of physics, basically what we are observing how a particular quantity changes when the other quantity is changing. This is what we are trying to observe. These load lines or these graphs in general, they are indicators of the variations. See, we cannot actually see through our eyes what is happening inside the device. It is not possible. We have talked about many things, the transistor, the diode, the majority charge carriers, the current flow. You cannot see the current flow in a transistor chip. Now, to analyze the variation in current, we need some graphical representation. We need some graphical or pictorial method to observe what is actually happening, and then only we can reach to some conclusion. This is the basic concept. And these are load lines. The word contains lines, means they are straight lines like this. And it is load here. Load means the resistance. What does this resistance, what does this mean? Whenever you have resistance R, then there is voltage drop, current, and we want to see the variation in these quantities. Load lines are very important in transistor or in semiconductor analysis. So let us start our discussion to understand what is a load line. Now this is a circuit that I have discussed in the previous lecture also. You can again identify it is a CE circuit because the emitter terminal is grounded. Here you have the base current, and this resistance, it is the base resistance through which the current is flowing. This is the collector current, this is the emitter current, this is the base emitter voltage for forward biasing the base emitter junction, this is the collector emitter voltage. The importance of this collector emitter voltage was discussed in the previous lecture. You can watch that video. Now let us move to our discussion. So, the first thing that we will discuss, it is called the DC load line. DC load line. Now this DC load line, it is simply a mathematical analysis, and it is very simple. Because you have studied coordinate geometry, you know the equation of straight line and all those things. This video may be a bit longer because this is a very important concept. So please concentrate and try to understand. Now we have to draw a DC load line. How can we draw the DC load line? To draw the DC load line, what we require, we require to know the cutoff and the saturation points, and I discussed the cutoff and saturation points. We need to know the cutoff and saturation points and saturation points. Now let me write it in a different color because this word I will emphasize on. Points. I am not talking about region. I am talking about points. We have discussed the cutoff region and the saturation region. The saturation region is that region where both the base emitter and collector emitter junctions are forward biased. The Cutoff region is that region where both the base emitter and collector emitter junctions are, and the base collector junctions are reverse biased. In the cutoff, the transistor is in the off state, it is not conducting any current. In the saturation region, it is conducting the maximum current. Now we require the transistor for amplification purpose, and these two regions, they are not required for amplification, they are required for switching purpose. We will study the switching property, switching action of transistor. So let us concentrate on our topic of discussion today. So this DC load line, if someone asks you in the Viva, what is a DC load line? Now suppose if you have this question, what is a DC load line? Suppose you are preparing for Viva in the practical examination, and the examiner asks you, what is a DC load line? You do not need to draw any diagram, you do not need to describe a lot of details, just you can answer in a simple sentence. DC load line is a straight line, that joins the cutoff point and the saturation point. Cutoff and saturation point. These 2 points are joined by this line, and this is the DC load line. This is the simplest answer that you can give when you are asked in the examination. Now we are considering the CE circuit, the circuit diagram I have shown you in the previous page. Now if we are asked to draw the DC load line, what will be the DC load line and how it will look like, and the most important thing is what is the explanation of this graph. Let us try to understand. So basically the DC load line plot is this one. You can get this diagram in any textbook, whatever you have that has a transistor topic. Now let us go into the details. As in the previous page, I talked about saturation point and cutoff point. Saturation point, I am not writing region, and you must know the difference between point and region. Saturation point and cutoff point. These are 2 points. Okay. Now the first thing is that how to locate these points. How to locate these points. This is the first question, then we will come to the line. Now observe this graph. This graph has X on the X-axis collector emitter voltage, and on the Y-axis this is a collector current. So it is basically a voltage current graph. Voltage current, or you can say current voltage graph that you are used to study with. Now how to locate these points? To locate these points, we will make use of the equation that I discussed in the previous lecture to locate the cutoff and saturation points. Cutoff and saturation points we use the equation. We use this equation that I discussed in the previous lecture. That is the relation between collector emitter and collector biasing voltage. VCC is equal to VCE plus ICRL. This is the equation. Now what you need, you have a graph of this kind, you have to plot a current voltage graph. The x-axis is VCE and the y-axis is IC, and you have to use this equation. This is the equation that you will use. So what we have to see, we have to change the equation a small bit. so that we can get the quantity on y-axis in terms of the quantity on the x-axis. So this IC will be VCC minus VCE by RL. This is evident, or you can write it more simply as VCC minus VCE by RL. This is the equation for current, collector current in terms of VCE, because you are varying this VCE. Now we have two situations. How can you imagine the two situations? If we are considering the cutoff means collector current is 0. Ideally this is collector current is 0. And in this case I discussed in the previous lecture that the collector emitter voltage, I discussed the importance of CE. In this case VCE is equal to VCC. So what you have, let me again paste this diagram on this page so that it is convenient for you. IC is 0 means y coordinate is 0, so it will lie in the x-axis. Now you see the equation number 2 of the previous page. IC equal to 0 means left hand side is equal to 0, VCC upon RL minus VCE upon RL. So if you equate this equation, you are getting VCC equal to VCE. So one point, the cutoff point is on the x-axis that you can determine. This is how you have determined the cutoff point, not the region. Region was in the characteristic. This is the cutoff point. This is how you can locate it. Now let us come to the saturation point, and I explained to you in the last lecture what happens in saturation. What happens in saturation? At saturation VCE is 0, collector emitter voltage is 0. So from this equation IC equal to VCC by RL, this is the maximum current that will flow through the transistor. It is in the saturation state. This current is not going to increase, so it is saturated. So this is the saturation point. And obviously if VCE is 0 means the x coordinate is 0, this point IC is going to lie on this point. This is IC at VCE equal to 0. VCE equal to 0. Now when you join these 2 points by a straight line, sorry, it is called the DC load line, because you have the load here. RL load resistance is here. When we join and they are designated in the diagram as A and B. When we join, cutoff and saturation points in saturation points A and B, saturation points A and B, the line AB is called the load line. This is the load line. I told you in the previous lecture that saturation point and cutoff point are two extreme states of the transistor, and in between whatever lies, it is the active region. So you have this straight line. I am drawing a rough diagram over here, and I can justify my statement that they are extreme points. This is the DC load line, this is A, this is B, this is cutoff, this is saturation, and whatever lies in between is the active region. We are interested for amplification factor in this active region. This is the diagram. All the points C, D, E, they are lying in the active region. C, D, E are points between A and B that are lying in active region, that are in active region. And in these points we are interested because the transistor works as an amplifier when it is in the active region. Now the slope of this line is 1 by RL, slope is minus 1 by RL. So it depends on the load resistance, that is why it is called a load line. Slope of the line AB, slope AB is minus 1 upon RL. It depends on the load resistance, that is why it is called load line. This is the significance of the load line, the most simple explanation of the load line, DC load line. It is a straight line. You can see, you know this much of mathematics, and I think you know more mathematics than me. So this is a line with slope minus 1 by RL, and the intercept is VCC upon RL. Now what we are interested in? We are interested in the active region. I told you what is the active region, why it is called active region, because this is the region where the output current is responding to the change in input current. At points C, D, E, the output responds to the input. So it is active region. This is the active region. We are interested in this region and we are going to analyze this region. In this region, the emitter, now what happens in this region, what if someone asks you what is the biasing? So in the active region, emitter base is forward biased and collector base is reverse biased. This is the biasing. Here both are forward biased. Here both are reverse biased. In between, one is forward biased and the other is reverse biased, or you can say the input is forward biased, the output is reverse biased. This is the condition we require for transistor action or amplification. This is the thing we require. Now let us come to the analysis. What more we can conclude from this diagram? Now, in these situations, another most important term that comes in the transistor analysis is called the operating point or the quiescent point. Operating point or quiescent point. Quiescent means static. The word quiescent means static. It is not moving, stationary. You can also say stationary. This is the meaning of quiescent. Now we are interested in the operating point. What is the operating point? Suppose someone asks you in the Viva what is called operating point. Now it is a point on the load line which represents the value of collector current and collector emitter voltage that exists in a transistor circuit, or that is present in the transistor circuit without any input signal. This point is the point on DC load line where the current IC and voltage VCE and the voltage VCE values without any input signal. Means if you do not have any input signal, then the values of current IC and the voltage, it is the quiescent point, have values without any input signal. This is the definition of quiescent point. So basically what you can conclude is that quiescent point is a point with a particular value of current and voltage. So if we consider this graph and suppose D is our quiescent point, it may be ABC. We will discuss the position of the quiescent point shortly. Suppose this is the quiescent point Q, I am denoting by Q, so it has coordinates VCE and IC. These are the coordinates. So what does this coordinate tell you and why it is important? So now we are interested in finding what is the importance of this quiescent point. Why we are required to find this quiescent point? This is the important thing. That if you are drawing the graph, it is not all over. You have to understand what is quiescent point. So what we have concluded, quiescent point Q is the value of IC and VCE at zero input signal. Input signal means input voltage or current. Input signal. This is the quiescent point. So it is a particular point with two coordinates, abscissa is VCE and ordinate is IC. So this is the definition. It is also called the DC operating point or the working point. Now why it is so? DC operating point or working point. Why it is so? Because it is this point which determines the working of the transistor. I am writing Q point for quiescent point is also called DC operating point or working point. It determines the working of the transistor, how it will work. It will work as an amplifier or not. DC operating point or working point. These two terms are also used for the analysis of DC. Quiescent. So this is the definition. Now we have understood the definition of quiescent point or DC operating point or working point. Now what does this point tell you? This point tells you that at which position in the active region the point should be located so that your transistor acts as an amplifier. The position of the Q points, the position of the Q point determines the working of the transistor. Determines the working of transistor. Now in the last lecture what we saw as the importance of VCE, that it is VCC by 2. For amplification the VCE, it should be half of the VCC. Now from the diagram that I have given you, the graph, this is the graph, you can find the value of VCC at this point. This is the value of voltage. Half of this voltage you do 1 by 2 of this value, and 1 by 2 it will lie somewhere here. So the best position of Q point, so that the transistor acts as amplifier. So that the transistor acts as amplifier. Amplifier is at the midpoint of DC load line. At the midpoint of DC load line, this is the best position. This is the position where the transistor will act as an amplifier. Amplifier is at the midpoint of DC load line. We can also examine this, or we can also prove this. We will see how we can locate that Q point for several circuits. Now this, we will see it later on. First of all, let us understand more about the importance. Now the position of the Q point on the DC load line, it determines the maximum signal or the maximum output that we can get from the circuit before. Some clipping, we have studied about the clipping circuit. Clipping means some portion of the input signal is cut off or it is removed. This Q point is so important because its position tells us how much maximum signal that you can get from that circuit in undistorted form. Position of Q point, position of Q point shows the maximum undistorted output. Now what is this undistorted output? We will discuss output that we can get from the circuit. We can get from the circuit. So we will study this in the next lecture, that how this position of the Q point determines the shape of the output signal, determines the form of the output signal, because we want proper amplification, not improper amplification. So what is proper amplification, or more correctly faithful amplification? We will study these things in the next lecture. For the time being, please stay connected and watch, like and subscribe the video channel. It is for you. It is for your betterment. Thank you.